An oracle can predict the future and give advice for what to do next. A mathematical oracle would be able to solve all of the big open problems in mathematics for us. The big surprise is that such an oracle really exists. It's a number called omega. If we can calculate its first few thousand digits, we can solve almost every open problem in math. That sounds extraordinary, but it also sounds too good to be true. So we will see how far we can take this idea before it breaks down. We are celebrating a special occasion today. You know, since the beginning of All Angles, I have always urged you to keep learning, to keep exploring new territory and look for interesting connections and concepts. One of the channel's most loyal fans, who has taken this to heart more than anyone, is my dad. And today, the day that this video is going live on YouTube, is his 75th birthday. If you want, you can leave him your best wishes in the comments. And if you'd be willing to share some personal information, tell him where you're from, so that he gets birthday blessings from all over the world. I'm sure that will freak him out. I definitely got my interest in math and science and programming from him. He's a retired software engineer, so we are going to talk computer science today. Here's a simple Python program that produces the first n square numbers. Even if you're not familiar with Python, it should be easy enough to understand how this works. We have a function that receives a value for n, and then it loops from 1 to n and produces the corresponding square in each loop. The variable I is just a small counter that keeps track of how many loops we've already done. The program automatically stops after doing exactly n loops, printing exactly n squares. Here's another example. This program produces the factorial numbers. And here's a function that gives you the decimal digits of the number 1 over 7. Since 1 over 7 is a rational number, its digits simply repeat forever. You can probably think of many more programs that produce interesting integer sequences. And what you might already notice at this point is that these programs are very small and simple, and yet they can produce arbitrarily long sequences. So we are getting a lot of bang for our buck here. We can compress long sequences into short programs. All we have to do is run those short programs on a computer to recover the much longer sequences. The Russian mathematician Kolmogorov realized that you can use this idea of compression to define randomness. When a sequence contains a lot of structure or repetition or patterns, we can exploit those to compress the sequence into a very short program. When the sequence is random, however, we can't compress it, and we basically need a program that contains the entire sequence and just prints it out. So, according to Kolmogorov, random is a synonym for incompressible. This is a really subtle and interesting way to look at randomness. Remember that scientists, and physicists in particular, are always looking for simple laws that can describe the universe. If the laws were insanely complicated, we wouldn't be able to say that we really understand the universe. If you measure a set of points, you can always find a curve that runs through all of them. But what you really want is a simple curve. I compress, therefore I understand. Rational numbers are very easy to compress. Their decimals just keep repeating, so your tiny program can simply loop them as long as you like. But most real numbers are not compressible. That's basically because there are many more real numbers than programs, let alone short programs. Each program is just a sequence of instructions. By systematically writing out all possible sequences of instructions, we can make a list of all programs, at least in principle. As soon as you can make a list of some kind of objects, we say that the objects are countable. The natural numbers are countable because we can list them. Python programs are also countable. But real numbers are not. If you managed to produce a complete list of all reals, you could always easily construct a new real number that differs from the first one, from the second one, from the third one, and so on. Because it differs from every number on the list, it cannot be on the list. This is a contradiction, which proves that such a list cannot be constructed. This is Cantor's famous diagonal argument. The real numbers are not countable. The conclusion, for our purposes here, is that there will always be infinitely many more real numbers than programs. And so if you think of the sequences of digits of those real numbers, the overwhelming majority of them are incompressible. They can never be produced by a program, let alone by a short one. But here is something weird. Even though there are infinitely many real numbers that are random, it's incredibly difficult to find one of those random numbers. The reason is again quite subtle. If you could come up with a definition for a random number, that definition could then be used to produce the number, to output its digits one by one. You just write a short program that basically translates your definition into Python. And that would mean that the sequence of digits is compressible. So your number isn't random after all. To put it very simply, as soon as you have a short definition for a number, you have typically already compressed it, so it can't be random. I realize I'm skipping over some of the details here. Our definition of randomness can be made much more formal and precise. But here I just want to give you a quick impression in order to get to our mystery number omega. It's going to be one of those rare random numbers that can be very accurately defined. But first, I want to give you a second angle on randomness. Let's say that we play a game in which you have to guess the next number in the sequence. If you guess correctly, you win money. Otherwise, you lose money. If the sequence was truly random, you would have absolutely no chance of winning any money in the long run. But when the sequence contains patterns, you can exploit those patterns to make educated guesses about what comes next. In this sense, a number is random if a gambler could never make any money by betting on its sequence of digits. Here are 3 sequences of zeros and ones. Can you predict the next digit in each sequence? The first one is easy. It has a repetitive structure. It's actually quite boring. It's like a perfect crystal, totally regular, no surprises. You could easily guess every single digit for as long as you want. The second row is totally random. I literally rolled a die to produce these numbers. There's no way to be certain about the next digit. It's a 50-50 gamble. Over the long run, you wouldn't be able to do better than break even. Interestingly, this kind of sequence is also boring. There's nothing interesting to learn here. The sequence is like static on a TV screen. It has nothing for your brain to latch onto. No patterns, no structure, just noise. The third sequence sits a little bit between the other two. There is some structure, but it isn't exact. You can predict with some confidence that the next digit will be a 1. As a gambler, you could probably do better than break even here. Every time you see a 1, you bet that the next digit will be a 0. Apparently, as human beings, we prefer an optimal level of predictability, somewhere between the bland repetitiveness of a crystal and the mindless chaos of static. John Allen Paulos compares this kind of sequence to a rose. It has a little bit of symmetry, but not too much. And now for something completely different. This little program sets the variable x to 5 and then starts looping as long as x is positive. It never changes the value of x, so x will remain positive forever. This means that the loop will never end. The program keeps running for eternity. By contrast, this other program prints a single number and then quits. Any given program must either halt after a finite amount of time, or never halt and run forever. For these two examples, it's easy to predict whether they will halt or not. But this is not so easy in general. For instance, if we start looping over all possible perfect numbers, and we print the first odd one that we find, will this program halt and print something, or will it run forever? As far as I'm aware, mathematicians currently don't know if any odd perfect numbers exist. So we actually have no idea whether this program will ever halt or not. That's an open question in mathematics. So it seems that we can often predict whether a given program will halt or not, but there are exceptions. The general question is called the halting problem. It was formulated by Alan Turing, the English mathematician who cracked the German Enigma codes during World War II. He proved that the halting problem cannot be solved by an algorithm. In other words, there can be no systematic procedure that can decide unambiguously whether a given program will halt or not. Turing proved that this is simply impossible. The idea behind his proof is really cool. Imagine that there was an algorithm that could decide the halting versus non-halting of any other program. You give our first example to this algorithm and it says, no, this program never halts. You give it the second example and it says, yes, this program halts. Now here's an interesting setup. This little program, let's call it G, asks whether or not G itself halts. It's a self-referential program. The question, of course, is, does this program halt or not? Go over the two possibilities in your mind before I give you the answer. Ready? Well, if this program halts, then this expression will be true, which will send the program into an infinite loop. So if it halts, it doesn't halt. That's a contradiction. The other possibility is that the program indeed doesn't halt. But that would make this expression false this time, so that the program never goes into the infinite loop and immediately halts. Another contradiction. This is such a cool proof. It revolves around a program that asks a question about itself. Applying things to themselves is a very powerful technique for debunking ideas and ideologies, not only in mathematics. I'm going to spare you the technical details of the proof, but if you look it up on Wikipedia, you will see something that looks like Cantor's diagonal argument. Whenever something refers to itself, there's a good chance that diagonals are involved. And now we are finally ready for the number omega. It was introduced by Gregory Chaitin, and it's very simply defined as the probability that an arbitrary program will halt. Now, out of all possible programs, most of them will do something utterly useless and then stop. So the value of omega is very close to 1. Its first few decimal digits are probably all 9s. Even though omega is very easy to define, it has some really interesting properties. In fact, you could say that it has a superpower. It can solve nearly all of the big open questions in mathematics. It's an oracle that can give us precise answers to many of the most pressing conundrums in math. That's quite a tall claim, isn't it? Let's see how omega pulls this off. The first thing you have to do is encode your mathematical problem as a Python program. We already saw an example earlier. Remember this program, which looks for odd perfect numbers? It encodes a mathematical question. Do odd perfect numbers exist? We don't know, but the question could be answered by finding out whether or not this program halts. If it ever finds an odd perfect number, it will print it out and halt. If not, it will run forever. In a similar way, many interesting mathematical questions can be reduced to the question of whether a particular program halts or not. Now, I can already hear your objections. Didn't we just learn that Turing proved that we can never solve this? It would mean that we have solved the halting problem. Well, yes, that's true, but the entire point here is that we have an oracle, the number omega. Its superpower allows us to tackle the halting problem. And we are going to make omega's job a bit easier. We are only interested in short proofs. If the proof of a conjecture is too long, we don't care about it. We want to be able to understand the proof, and that means that we can put a length limit on the proofs we will accept. What I want to show you now is exactly how omega solves the halting problem for all short programs. It gets a bit technical, so feel free to skim if you're only interested in the end result. The key is to write everything in bits, in binary digits, zeros and ones. The number omega has a decimal expansion in base 10, but it also has a binary expansion in base 2. Python programs can also be translated into binary by simply giving each instruction or each letter of the alphabet a unique code and just concatenating all those codes after each other. The precise translation mapping doesn't matter, as long as we can turn everything into bits. Since we are interested only in short programs, we will limit their length to n bits. N can be anything, maybe a few thousand bits for starters. We then also consider only the first n bits in the binary expansion of omega. So we just chop off all the other bits after the nth one. The resulting number, which we will call omega n, is slightly smaller than omega itself because we chopped off its tail. And omega in turn is slightly smaller than omega n plus 1 over 2 to the n. That's an important detail to keep in mind. With all this binary machinery in place, we can write omega as the sum of 1 over 2 to the k, where the sum runs over all halting programs of length k. The details are on the screen if you feel like checking them. Now, put omega n on one side of a scale. We're going to fill the other side with weights until the scale tips over. We begin executing all of the short programs. All of them. And we have to make sure that they all get a fair chance. So we run one instruction of the first program, then an instruction of the second program, and so on. As soon as a particular program of length k halts, we add a little weight of 1 over 2 to the k to the other side of the scale. Eventually the scale will inevitably have to tip over. Can you see why? Remember that omega is the probability that an arbitrarily selected program halts. But omega n is slightly smaller, so after some time, the halting programs will manage to contribute slightly more than omega n in weight. The scale tips over. And once that happens, no more programs shorter than n bits can ever halt anymore, because if they did, they would contribute a weight that would take us higher than the value of omega. And so at this point we know for certain that we have found all halting programs that are n bits or shorter. If our mathematical program that searches for an odd perfect number hasn't dropped its weight yet at this point, we know that it never will. The definition of omega forbids that. And so that would give us an answer. There are no odd perfect numbers. If, on the other hand, the program did halt, it would do so by printing an odd perfect number, and we would also have an answer. So you see that if we knew the value of omega, or even just its first n bits, we could answer questions about perfect numbers, twin primes, the zeros of the Riemann zeta function, and much more. I know that I went over the technical details a bit quickly here, but the main point isn't in those details. The main point is this. The first n bits of omega could answer all questions that can be encoded in programs of n bits or less. Omega is an oracle that answers the majority of open questions. Okay, wow, that's great. All we have to do now, in order to win the Abel Fields Clay Nobel Prize for all of mathematics, is determine the exact value of omega. And that is where we hit a brick wall. Turing's proof makes it impossible to solve the halting problem. And so we can't know the value of omega. We never will. But it's weird. Omega really is a number. We know its first few decimal digits. Maybe you have already written it down at some point in your life. But you will never recognize it for what it is. So here we are. We have a very precise definition for a real number. The number is totally random. It cannot be predicted or compressed. Its value would answer all of our questions. But we can never hope to calculate this number. The truth exists, but we will never be able to know it. There are no free lunches here, not even for wizards. That may sound like bad news to you, but actually I say we should be happy. Just imagine how horrible it would be if we could solve all math problems with the snap of a finger. Math would instantly become dull and pointless. The fact that we don't have an oracle makes it much more exciting. It means that we still have interesting work to do, things to discover, bridges to cross. We will just have to keep chipping away at the huge mathematical mountain, one tiny pebble at a time. So relax. There will always be more to learn.